Hey guys, how's it going? And welcome to another episode of Ferris Makes Hardware. It's episode 28, and we are still working on Verilog generation for kaze, driven by the Xenowing project. So, a little bit of updates. I don't actually remember exactly where we left off last week. I think I was still debugging the Uart receiver, and we tried to... It didn't work on the actual hardware, and we started throwing things together, some tests, and looked at some output. I think I had hacked together some waveform generation, and the waveforms looked really good. So I was able to continue that debugging into the weekend. And long story short, the Verilog generation was bad. In particular, what had happened was, this is some generated code, and there's a bit more here that I'll get to. But my font's a little small here, but it's actually easier to show in that case. Anyway, I found some of the logic here that would go into, for example, the next value for the data register. And it follows a bunch of conditionals that would basically either choose its old value or its new one. And I went and traced these sort of by hand, and everything looked pretty good. The one part that didn't, though, was this temp20. The idea here is that we take the previous value's upper bits and then we shift on the new bit from the receiver. And this way we treat this data register as a shift register that shifts in new bits as they come in from the transmitter. And the error happened to be actually not this code at all. This looks good. This is, again, Verilog syntax to concatenate two signals. So this one would be a 1-bit signal, and then this 6-bit signal, or sorry, 7-bit signal, which is these bits of the previous value. And the issue is actually this not this assignment, but the declaration of this node. And if I scroll up here, we can see temp20 is here, and this has 7 bits. But before, instead of taking for concat, I can actually show the code that was wrong in kaze itself. So in kaze, there's, for system Verilog gen, there's a little compiler in here. And for when compiling concat, it calculates the bit width of the resulting signal by actually asking the signal to give its bit width, because we already know that in the IR. However, because when I had wrote this, I was being kind of sloppy. I went with one of these additive ops where it just takes the left-hand side, and that's actually enough for the bit width, and copied and pasted that. So what ended up happening was that this was generated with a bit width of 1. So it looked like this instead. And Verilog has no issues with that, which is one of the reasons why I have a hard time writing Verilog a lot. One of the things I really don't like. Like, I like these kind of casts to be explicit. And in this case, it happily accepted that. And that's also why, I don't know if we actually looked around in Vivado on the stream, but I actually was never able to find the data register. And what was happening is that after synthesis, things would be optimized by the Xilinx compiler. And because if you look at this data register, I think it has a default value, or maybe this one doesn't. Well, regardless, if you take this data register and you only take some of the high bits, but not the very high one, and then you shift it, and then you truncate it to 1 bit. This 1 bit ends up staying constant. It never changes. Its value actually depends on what it was at startup, I think. But anyway, this ended up getting optimized away, the whole register, so I was never able to find it, which was kind of annoying to debug. But luckily, I got fed up because I keep saying that I don't really have a way to debug stuff on this board, and that is actually entirely untrue. I just missed the documentation to set it up, which I'm somewhat annoyed about because I feel like it should have been easier to find, but it's probably my fault for not reading the documentation well enough, and I'm happy to admit that. Anyway, as it turns out, I'll actually show this really quick. It's pretty easy to set up. So this board is a Numado Mimas A7, which seems to be a decent board. I'm fairly happy with it so far. It comes with this software called Tanagra, I think is how you say that. And I normally don't like software like this very much. I'd rather this was like a collection of command line tools that I could invoke to my liking. However, it has some nifty features. So I've been using this, like, I'll actually go back. So at home, you can see it detects my device because I have it turned on. I can select that, and in here I can, I guess, rename it. I didn't know I could do that. I can exercise the memory. I could look at documentation for this product. I can program the device, this is how I've been putting software on here before, is I would navigate to a .bit file, which is a bit stream that's been produced by Vivado, which I have here. So we can just, while I'm talking, I can open the Uart project. And then I would run it on here, and this will either program the SRAM or the flash memory. So the flash memory takes longer to program, but then it's non-volatile. And this will be loaded back in the FPGA when I reboot the board. Or SRAM, which will just run it immediately, and that's a bit faster. But also, there's this feature that I totally missed, which is this Xvc server. And Xvc, as it turns out, stands for Xilinx Virtual Cable. And this is actually a great feature because if you're using some of the debugging features built into Vivado, you need a particular kind of cable or whatever to actually load that onto the board. But as it turns out, you can run this Xvc server, and what this will do is this will emulate that cable so that here I can go into like the hardware manager. Oops. I just made it generate the bit stream again. Whoops. Oh, well, I think I can still open the hardware manager. But the idea is here I can open a target here. And so if I go to, for example, open new target, I can go to local server as long as I have this running here. And then add virtual cable and just connect to my local host on whatever port. So I guess you can use this to connect to remote machines too, which is pretty cool. And I think that should be working. There it goes. Now it detects my device, clock frequency and everything, and then I can finish on there. Now I think I don't have any debug cores instantiated in this device right now, and also I don't know why Synthesis just failed. That's a bit weird. Let's see. Data ready. Oh yeah, I changed some names of some signals, and I haven't updated the test, but we'll get to that actually because I want to finish porting more of this test stuff there. Anyway, then I can program the device from here, from Vivado. I can also like refresh it, and if there's debug cores, then I can instantiate those as well. So for example, we can program it by using an old bitstream file, which I think it doesn't have any now because now that failed. So I guess I'll show this flow a bit more later. But the point is it's that easy to set up, and I just totally missed it. And this was really valuable in debugging this because I could clearly see that after synthesis of the design, again, that register was gone, and then I could also look at like the other signals. And I could see that like all the timing looked good because just like we did in simulation last week, I was able to tap into different signals like the states that we looked at and saw that they looked exactly the same on the hardware, so it couldn't be that. And then eventually I was able to narrow it down to that code gen bug, which is great. Like that's kind of the best case scenario for where that bug was, because nothing else really made any sense to me. And I knew that code might be buggy because I just wrote it and I don't really have any tests for it because I still haven't figured out a good way to test that. Again, I thought about like taking a Verilog parser, which there are a few Rust crates that do that, and then parsing the output and then checking that against what I expect. But I want to be able to change the way we generate node names, for example, or the order we output declarations, things that don't really matter to the behavior of the generated component without breaking the tests. So I even thought about using one of those parsers, and then if you use a subset of Verilog, we could parse that and then actually convert it back to a kaze structure. And I'm kind of playing with that idea in my head, and I kind of like it. So I might do that at some point. And then this might end up being something that can ingest Verilog anyway, and I'm not really sure how I feel about that. But anyway, that's for another time. What we want to focus on now is another couple things that I want to talk about. So basically, a little bit of continuing what I worked on last week. I got that fixed. I got that code gen bug fixed, and then I was able to run the Uart test successfully I think I ran it overnight on Friday, which is great because I wasn't going anywhere because I don't know if you guys know this, but I guess most countries around Europe, at least now, have this kind of home quarantine thing going on, and Norway is one of them, so we've been affected by that as well, which hasn't changed my life much, practically speaking, other than I work from home more often. But yeah, this was a good Friday night, is my point. But once that was running, I was able to verify that. And then I also set up some additional test stuff. So what I did is I went in the xenowing itself. Let's see, let's go into the RTL project here. And yeah, the xenowing itself, and I was able to hook up the UART to the actual system again, which is really cool. So now I have this UART interface, and I hooked up the transmitter to that. And yeah, I also ported all of that. I ported the UART receiver, finished that, and I ported the transmitter, and I also ported the LFSR that's used in the Uart test, which we'll get to a bit as well. And then I hooked up the transmitter and the receiver to the xenowing itself. And then what I did is for sim, I actually wrapped that in another module. So I have the xenowing sim project here, and the build script for that creates a xenowing. And then it exports most of those symbols, just kind of forwards those to the output of this top level one. But a critical thing that it also does is, since the UART module has a UART transmitter and receiver line, to ease hooking this up to sim, I actually hooked that up to another receiver. So I hooked the transmitter from the xenowing to another receiver, and the receiver from the xenowing to another transmitter. And that gives me a byte-oriented interface to this additional top-level thing, which then I'm able to interact with a little bit easier in sim. So with that, I was able to hook up, it's just this much code to actually interact with that byte-oriented interface, which is really nice. So with this, I was able to hook up this kind of command passing so that a host could sort of talk to the xenowing over UART, and more importantly, vice versa. So the xenowing can actually talk to the host and, for example, request a file, which I want to use to load the boot ROM. So far, I actually should run this sim, because this is actually pretty cool. I got to change a couple things here. I know I've got a lot of things in flight, but I've just been making a lot of progress, and I'm really excited about it. So let's go ahead and go back here. So if we go into cd sim xenowing, I think I could just do cargo run -- release, and then I give it the ROM file, which right now is in rom.bin. Now, if I run this, it didn't take long to build at all. In fact, because I think it was already built, to be fair. And then you can see it says the XW online, and then attempted host file read. And so what this does, it requests a file from the host. And right now, I just kind of hack this together. There's no real smart protocol. It just sends a 1 out on the UART and then expects the host to send about a length of a file and then some data back. So then it waits until it gets that length in the data, and then it cats it. And so this what up, does this actually work? This is the xenowing running in sim, printing back some file data that the simulator host sent it. And then it just prints out some other debug stuff. So that's really cool. And the idea is that the host code is just going to use this sort of byte-oriented interface and like process commands. And then the xenowing, when it's running on the actual FPGA, is going to use this exact same interface. So that's why I wanted to hook all this up this way, and also why I've been spending so much time on Uart. Like, I think I've spent at least a couple of these hardware episodes where I wanted to work on one thing, and I ended up just debugging Uart, which is kind of funny. And in fact, if I want to take another stab at trying to make the Uart faster, now I actually know that I can use chipscope and these other helpful Xilinx features. So I might do that again at some point and try and figure out why it doesn't actually work if I run it faster. But yeah, we'll save that for another time as well. So what I want to do today, we're finally getting to that, is I want to continue on the Verilog generation in Kaze, because that's something we need before we can actually run stuff on the FPGAs. We need to be able to generate actual Verilog code for all the features that Kaze supports. And then all of the stuff that works here in Sim should mostly just work. It won't work as is right now because the xenowing itself actually exports the DDR3 interface and the BIOS ROM interface, which I've been calling the program ROM. I think I'm going to call it the boot ROM, actually, eventually, because it's not going to do anything other than just for the basic stuff to boot. So it's not really going to be a BIOS that you like call into to do low-level stuff. It's just going to have enough code to load the main program, and that's about it. But anyway, these aren't the final interfaces. I need to integrate the BIOS ROM into Kaze as well, which I think will be relatively easy. I just haven't done that yet. And then, yeah, hook up DDR3 again. But all of that, I think I want to do with tests that I can write in Kaze as well. And in fact, the way I want to test that is I've kind of been doing everything sort of piecewise. is I have this Uart test, and the idea there is that I have, well, now it's actually all in kaze, isn't it? Which is cool. Most of it, at least. I have this LFSR, which I think someone asked if they were encryption. By the way, I'll say hi to all you guys in a second. Sorry about that. But the idea is that I use an LFSR to generate a big random string. And then I send that out on the transmitter, and then I have a program on the host that just sits there and waits for that stuff coming in, and can also run the same LFSR, so it can check that all of the data that's being sent out of the FPGA is correct and in the correct order. And then we'll also echo that back, so that there's also a receiver data path on the FPGA that also runs a separate LFSR, and so all the data bytes that it receives, it also checks. So if at any point either the transmitter on the FPGA or the receiver on the FPGA or the receiver on the host gets wrong data, then one of them's going to complain about it, and then we know that the UART actually doesn't work. So that's the test that I've been like sort of guinea pigging everything with, because it's actually complicated enough to cover a lot of features in kaze. And it's also pretty critical, because I want to sort of use this as the main transport that I have to actually talk to the device. Later, I might end up trying to bootstrap something that's more complex, but I'll do that via this interface as well. If I want to try and write like an Ethernet driver, for example, then I will expose some ports so that we can talk to the chip that I have on the board here, and then try and sort of bootstrap it like that, which I think would be effective. But it'll take a while till we get there. Anyway, I started porting some of the code for the test on there, but the thing that I haven't done is there is this UART thing here, and this is the code that actually ties it all together. So there's a UART TX, which comes from kaze. There's this LFSR, which again comes from kaze. There's the UART RX, which comes from kaze, but all of this top level stuff does not yet. So I want to replace this UART module with one written in kaze, which should be relatively easy to write. However, the reason I didn't do it yet is because one of the features I haven't implemented yet for kaze is the ability to compile system Verilog when you have instantiated modules in the kaze code. So that's what we need to work on. And again, I think this is a good way to kind of test that feature with a relatively simple module rather than the xenowing itself, which is a lot more complex. So that's what I want to work on today. Anyway, I had a guys in the chat. Zakor, Mad Moose, Dark Second, thank you so much for the sub. That's awesome. Anarchy, SK Test, Chief Detector, Shodrin, Wistertobe. And let me catch up with what you guys actually wrote as well. Congrats, Dark Second, on building a new PC. It's a good thing to do while staying inside. Oh yeah, Shodran, I'm sorry if you expected today to be a demo scene stream, and that's why you did the sad faces. But by the way, I wanted to announce, and I'll announce this again and on Twitter. I think it's going to be 1 p.m., so 13 CET this Sunday, right? So I'll get the date on that. But anyway, that's when I want to start doing demo scene streams. So at least for a little while, I want to do demo scene streams as well as emulator or hardware streams or whatever. So I'll bring back the Sunday streams, but I'm going to do them earlier in the day. And there's a couple reasons for that. One of them is, I don't know, I kind of want to. Another one is that Tropical Trevor of the group Pooh Brain and Tom, CPDT of Monad, are some guys that live a lot farther east. And I would like them to catch the streams as well, because I know that they also do a lot of interesting tool work. And especially Trevor, I know that he and I are aligned a lot with ideas, so I think it'd be cool to have him on the chat. So that way I can accommodate some of that audience as well. So yeah, 1 p.m., 13 CET this Sunday. And I'll do more announcing on Twitter as well. So that's, I think, the 22nd. So I think that'll be pretty cool. So yeah, so those will make a comeback at least for a little while. And I think that'll be really fun. And the other reason I wanted to actually bring back the demo scene streams, obviously there's this like social isolation thing. Or social distancing, isn't that the term? So I've got a little more time where I'm going to be at home for sure. And also, cool, Dark Second, look forward to it. Also, I just want to work on some demo tool stuff. I hadn't really planned on doing a lot of demo scene stuff this year. I don't plan on really doing anything for revision. Although they're actually looking into doing remote seminars, so nothing's set in stone there, but I have expressed interest, so we might work something out for that. Anyway, I had planned on doing a production, but it's actually Solskogen's last year this year, and after we found that out, but before we found out about the virus, we had planned on maybe doing a thing for that too. So I don't know what the status of that's going to be. That's up to them to decide if they're still going to have that party in July or not. But if they are, Logicoma might release something. I think that'd be really cool to throw together for a party that's been very good to us over the years, especially me personally. But yeah, we'll have to see if that actually happens. But either way, there's some demo tool work that I want to start working on. I don't think I've done any of that since like last May. So I think it'd be cool to do that on the stream. So yeah, so that'll come back on Sunday, at least for a little while. And I'm looking forward to it. Okay, a lot of talking. But yeah, I'm happy with this progress, especially getting this file thing to work in Sim. I want to show some of the code for that because it's relatively straightforward. So there's two pieces of code that are important here. There's what actually runs on the xenowing itself, and that is in this currently. Again, it's still in the ROM directory, but we're going to split this up because the ROM is actually going to be, there's going to be ROM, and then there's also going to be the main program that runs on there. And so we need to split that up. But if you look at the main program, you can see I have this XW put s and like display in it, which doesn't do anything right now. So yeah, so right now I just added this test code, put s attempting file read, and it writes out a 1 byte to the UART. Another thing I changed is that when you actually do put c, it actually prefixes every character with a 0 byte, and that's a command to print a character, which halves the bandwidth if you're going to be printing text, but I don't care about that. So yeah, so we write out 1, and then we expect that the host is going to bring back or give us like a length and everything for the file. Eventually, this interface here, or this protocol here for requesting files needs to be expanded. Like I need to be able to write out file name and then expect or load an explicit file. Maybe there's some compression here that I'm going to do. Who knows? But the idea is there. So we add a command, output a command to read a file, and then it's going to send back the length of the file, which I then print out, and then the actual bytes, which I stuff in a buffer right now, which also needs to be dynamic. So we need to do a memory allocator at some point too, which I also hope to debug via this UART interface. So that'll be pretty fun too. And then after that, prints out successful, and then just cats it. So it's as basic as it gets. But still, it's really cool to see this actually works. So quite happy about that. Rust Analyzer, I haven't checked that out, but that sounds familiar. Is that the perf stuff? Oh, compiler in front of for IDs. Totally thought this was something else. No, I haven't checked that out. I still need to make the switch to VS Code on this machine, though. But yeah, I think I mentioned this before, but one of the reasons why also this loading files over the UART is really important is because it's going to load sort of the second stage, the actual program. And also I'm going to use that mechanism to reload. So I want to have like a reload command that the host system can send to the xenowing, and if the xenowing is doing like a message pump thing, it will interpret that message as it needs to reboot. And then I think I'm just going to have it jump to like a reset vector, and then it's going to run the boot program again, and then that's of course going to load the file again. So I think that'll be a good way to do this. That way we get like the ROM reload as well. The other thing that I did when I implemented this, because I had implemented like a general purpose FIFO for all the bus stuff, I stuck one of those between I can actually just show you. In the interface to the UART, I stuck a receive FIFO. So this is actually the thing that's being written into by the UART receiver, and then when you pull data as a user, you pull data from there. So there's this. What did I make that interface look like? ROM. There's so many files here, you guys. Big project. Or still not that big, but a lot of stuff. So Uart, no, here. There's a status register, and the lowest bit of that will tell you if there's characters you can read. And then this RX read will actually pull a character off of that FIFO. So then if you want to read a byte from the UART, that's what it does. It just waits until there's a byte available, and when there is, it reads a byte from there. And I also wrote getC here, which just does that. So this will be nice. That sounds really nice, shift detector. Yeah, and then there's also this host side code, which again is pretty basic. I actually ran the simulator in another thread and then added these channels to send and receive from there. And one of the reasons I did that is because it just kind of, it does all this buffering for me and everything, which I guess I don't really need. But I kind of wanted to write this like main loop here where it processes commands sort of agnostic to what's actually processing the commands. Because the idea is that right now I have this, like these channels here, but maybe I put this behind a trait, which is like a device trait, so you can send and receive from it. And then I could implement that. One way is by backing it by these channels and running the simulator in another thread, which is what I want to do. And the other one I could do is actually back it by something that interacts with the COM port, and that's how it would actually talk to the device. The same code would be used for both. Which I think is really important, because I think when like doing small tweaks to the hardware and like checking registers and stuff, the workflow should mostly be in sim, because that's actually really fast. And then it should mostly just work when I move it to the device, and then that's where we're actually going to get full speed for things like the rasterizer. So supporting both flows is going to be really important. And I also want to have commands that I can send to the device where that would allow us to, I don't know why I'm losing my train of thought here, but allow us to do things like read and write memory and read and write registers, which I also want to use to test most of the new hardware once I get that working. Yeah, so let's get a bit focused here. And I might make my font size a little smaller because I'm going to be working on code gen stuff. I may need some of that. So what we want to do, I think, like I said, I wanted to port this Uart test. So I actually added two modules here too, because there's this Uart module and then a module that I call top. And there's an important difference here, because Uart just puts all the test stuff together, and then this top module adds, for example, the sync chain for the reset and the sync chain for RX, which will synchronize the reset signal and this RX signal into the designs clock domain. And this is the kind of thing you would do sort of per device, most likely. So I like to keep that in Verilog, but then I want to just instantiate the test itself and have this test be something that's generated by kaze, which I think makes the most sense. But again, it doesn't work yet because I don't have these instances supported in CodeGen right now. I'm probably going to change a fair amount of stuff in the system Verilog compiler. Oh, another small thing is I was originally going to generate Verilog, and I was going around between versions, like probably Verilog 2005 that I was going to generate. But then when I was reading up more on Verilog, I was reading that it's pretty much all been absorbed into the system Verilog spec. So then I thought, okay, I'm going to do like system Verilog 2001 or something and just stick with that to pick a version. But someone on Twitter pointed out to me that Yosis, which is like the tool for open source FPGA development, if you're going to use any of these open source flows, I think the front end is always powered by Yosis. Yosis only has official support for Verilog 2005. So I'm going to go back to that actually, which I'll do later. Like right now I'm going to continue what I'm doing, generating system Verilog, and then I'm just going to change it to do Verilog, which shouldn't be much different from the perspective of the compiler, I think. Mostly just syntactic changes for the basic stuff that we support. So I want to change that, but we'll do that as another thing. So I was a bit surprised about that. I thought system Verilog was what everyone had kind of landed on, but I'm more than happy to change that. Like it's really no big deal when we generate the code anyway. It's a nice advantage of having this kind of approach. But yeah, I'm going to make my font a little smaller here, and we're going to look into generating the correct code. So the first thing I want to do before I actually generate the code is port this UART module to kaze. And then we won't be able to test the port until it all works. So that's going to be kind of annoying, but I don't think it's going to be terrible, actually. So the first thing I'm going to do, actually, is I can close this hardware manager thing here. And I also seem to have a lot of issues with this virtual cable server in Tanagra if I don't shut that down. Oh, it's crashing. So that's the other reason I don't like this Tanagra stuff, is that it crashes all the time. We'll reopen that later when we have to. But in here, I'm actually going to remove this Uart SV file here. And so now, yeah, now this is basically broken. But we still have the file left in our file system, which is important. And I also have to go back. Oops. A couple things here. I also have to go back and change some of this. So I'm going to move this down here so I can have that. And then we're going to write the port. And I think also in this RTL thing, I have to go back to this other sort of unpublished version of kaze, which I'm actually using to gen the code. So we'll go back in here, and I think we just do cdrt. No, I think I can actually do make generated RTL. Yeah, and that, again, just runs this RTL, so I added this main file here as well, which just generates a few of these modules into this generated.sv file, which will eventually be a generated.v file, but we'll worry about that later. So yeah, so to add this, we will do, it's called Uart, but maybe we want to organize this a little bit differently. In particular, I think I might want to mirror this kind of organization where I have the name of the board and then some test stuff. And I think that might make some sense here. So if I actually do mod mimos A7, then I can put, for example, this LFSR is specific to that. I might as well put that in there. Let's do that. So now in modern Rust, I think I can do new file mimos a7.rs. This will have an LFSR mod. And then now I can make a new directory here. And I think I actually want to go one just to mirror this structure. I think I might want to do pub mod test. And in here we can do test.rs. And there we can do LFSR. So we'll do a new file in there. Actually, I think we can do a new folder called test and put it in there. That's what we want to do. But yeah, test LFSR. Yeah, so this will be lfsr.rs. I think that's how I want to do this. I might move this stuff around later. I don't care. But yeah, this is going to be all this stuff. So I'll just delete this file. Move it in here. And that should be good. And now I think main will break, because this uses LFSR. I think we actually want to do mod mimos a7. And then this will be a7 test LFSR, which it actually won't be. It'll actually be test Uart in a minute, but we'll just run this to make sure the organization works. Took a bit longer than expected. 10 seconds to do that. That's kind of crazy. Don't know why that took so long. But probably a fluke, because it's really this run here. That's where it's actually running all the kaze stuff, which is shit fast. So that's good. Let's see. So we're going to add a Uart Mod here. And just like with LFSR, it's just easier if I copy this. We're gonna do this. We're gonna call this Uart. Easy. And also what I wanna do is on the top level stuff here, I'm gonna change this. Okay, looks good to me. I think actually I do also need to have the LFSR thing here when I think about it. Yeah, and now if we open generated here, there's the LFSR, there's the UART, which is empty, but it's there. And then the UART receiver and the UART transmitter, which we need all of these generated like this, so this looks good to me. And then we're going to actually port the module. So let's see, we need actually nothing imported here. So the main thing that this has, it has a single register, which I'll actually start with. So let has errored is m.reg, that's called has errored, and it's going to be 1 bit. And it's going to have a default value, which is false. And this is actually kind of cool because we can generate this. We don't have to, but it's kind of cool to see. And now because I have a register and a default value, I don't know why that takes so long. Oh, look at this. Even gave me an error. Cannot generate code for module UART because module UART contains a register called has errored, which is not driven. That's true because we didn't drive what its next value is going to be. And I'm not actually sure. Well, for now, we'll do this. Drive next has errored. Not going to be correct. We'll do that. Oh yeah, that's dot value here. There we go. And now, oh, it was optimized away. That's funny. So it's validated and it generated code, but it didn't do anything. So I guess we'll have to make that do something later. But actually, we are going to want to output this. So let's do that. m.output, and we're going to say has errored, and that's going to be has errored.value anyway. So this actually we do want. And then we should see the register there. And now we do. You can see it generated this has registered and next. And it assigns the next value to its current value. And also it outputs the current value. And then you can see if reset is asserted, it resets this to 0. Otherwise, it sets it to its next value every clock tick. Perfect. So I think I'm going to start with this LFSR here for TX. So this will be let LFSR TX, or actually called it TX LFSR, is m.instance. We're going to call this TX LFSR. And it's going to be called Uart TX. Or that's not true, actually. This is going to be LFSR. And we want to set up the value for the LFSR. Or actually, we're going to get that out, and then it has this shift enable too. So we're going to need a couple things here. So first thing we're going to do is let write enable. It's going to be not has errored. So if we haven't errored, we're going to continue writing. And that's important because for this LFSR, we need to drive its input. And in this case, we can do shift enable for whether or not it's going to generate the next value. And this is going to be write enable and write ready, which I don't think we have yet. Oh yeah, that comes from the actual UART TX. So we'll do that. Let TX UART. Or actually, we'll call this UART TX like it's called in the other one. This m.instance. Like that. You can see here I've also adopted this style convention where instances are, and most other things are this snake case, and then otherwise it's, I think this is called Pascal case, where it's camel case, but also the first letter is capitalized. So yeah, we'll make that, and then we'll do uartx dot. Yeah, I think that's a subtle difference. I think this is technically called Pascal case, and this is camel case. Could be wrong. Yeah, also this has error dot value, and then uartx dot. Yeah, exactly D single 12, if I read that correctly. So we want to drive uartx's actually something else here. This write ready. Yeah, write ready we can just pull off there. So this will be uartx dot output ready. Essentially, if we're asserting a write and we know that the output was ready, then we can shift this. Otherwise, we need to wait. So uartx dot drive input. That's what we need, and this should be enable, and then that'll be write enable. And we'll pull out the data from this later. But I think that's all we need to hook up here, except TX. We definitely need that. And this gets really easy because we can just do m.output TX, where we take the uartx dot output TX. That's great, Chief Detector. It's good when you learn on the streams. That's all I try to do, is learn on the streams. So this might be the whole write path, actually. Except the data, right? Yeah. We need to actually output the data. Because the data that's going to be written, uartx.drive input, and this will be data, and that will come from the tx LFSR dot output value. It's called. What did I break? Is that it? Cool. Yeah, kebab case is great. Probably my favorite of those names. So again, we don't need to generate this now, but I like to do this because I like to sort of sanity check what we have so far. Because kaze will throw us errors like attempted to instantiate a module identified by uartx, but no such module exists in this context. And that might make sense because we need to make sure that this has been generated first before we can generate this. And I'm guessing the top level code here does not generate these in the order we expect. So we actually need to do this up here. Like that, for example, in order for those modules to have been generated within the same context before we start generating code for this. And now it says not yet implemented, and that's probably because we have an instance. So this is not a normal error that's going to come out of any release version of kaze. If you see this in a release version of kaze, it is a bug. Although right now, it's just that we haven't implemented instances. So I didn't really think about that, that we actually can't generate code for this because of that, but we'll be able to soon. That's what we're doing today. In either case, it's actually kind of comforting that it got this far. This is still useful information because this meant all the validation passes did succeed. It's just that the actual generation itself did not work. So still happy we tried that. But yeah, let's do the receive path now. So we're gonna do let uart rx is sim.instance uart rx. That's gonna be a uart rx as well. And we'll also do uart rx.drive input, which is gonna be called rx, and we'll do m.input rx, which is 1 bits. So sort of forward that value. And then yeah, this UART will have some other things. So let read data ready. Or let's do read data valid. I like that better. We can do this. Let read data is UART rx output, and this will be, I think it's just called data. And this is UART rx dot output data ready. I think actually these are called data valid now, which is why I think this test didn't build when I tried it earlier. No, I'm not using Rust Analyzer. I'm using good old Rust Enhanced and Sublime here, which I think, I don't remember what it uses. The name of that's escaping me, but the old thing that everyone used for a long time. Yeah, RLS. Thank you. Exactly. That's great, Chief Detector. I definitely need to do that. But yeah, I think that's all we need to hook up for the receiver here, and then we can also do let rx LFSR. So again, we're gonna do another LFSR instance on the receive path, and drive input, shift enable, and that one's gonna be whenever we get new data. So that's read data valid, and then yeah, then we also have the value there, which we'll get to here. So has error. This is the interesting part, really. Here we'll do an if here. We'll just drive the next one like this. We'll do if, and ifs in kaze look like this right now. So if read data valid, then this is going to be read data dot ne, so not equal to, we can do rxlfsr dot output value. So it has errored if these are not equal. And then if read data is not valid, we need this else case. And so for that, we'll just do has errored its current value. So we'll keep its value. And I think this is it. So ooh, implicit types and refactoring. Both of those sound really nice. I miss that stuff when working with Rust. I've learned to cope without it for years, but that doesn't mean that I'm having a better experience. So should definitely check that out. Okay, so again, this says not yet implemented, which means all the validation passes worked. Now I want to do a quick comparison here, by the way. If you look at, this is the Verilog code. So just the immediate thing that stands out, 73 lines, and the equivalent in kaze, which, disclaimer, since we didn't actually generate valid code, I can't really claim that this is exactly equivalent yet, but I think it is. And this is literally half the lines of code. Okay, maybe not literally, because 36, actually that'd be 72. So it's, yeah, just under half the size. It's a bit denser. I think readability is okay here. I mean, there are things that are duplicated, which I don't like. And like this if thing can be considered a bit ugly. I do like that it's forced to become expressions here, but I don't necessarily like the syntax. I might come up with a macro for that. I'm not entirely sure. One of the things I do like, though, is that like this register logic, I think, is a lot simpler here. And one thing I think that the Verilog does better is it forces you to have all the ports here, which if you're looking at this, you see these outputs are sort of scattered within the code, and then also there's inputs to this, which I think is only here. And so it's hard to sort of glean what the inputs and outputs actually are here, which I'm not a huge fan of. So what I want to do is come up with sort of an idea where you can have, for example, Spinal HDL and Chisel have these things that I think are called bundles. And then those are essentially just groups of signals. And the idea is that each module has like an IO bundle, which defines its inputs and outputs, or declares them, and then you have to drive them like you would an input and output to a module or a module instance. So I might adopt something like that at some point, which would, at least given a piece of RTL like this DLFSR as well, where it sort of has the same thing where this is where one of the inputs is, and then has this output value, and it's you don't necessarily want to dig through the code to find those. So I want to kind of fix that. But those are like language enhancements that I think I can do just on the front end. And it may be that I end up sort of completing the xenowing without doing that, but we'll see. We'll see how fed up I get. It might be one of those good enough is the enemy of, or what is that? Like one of the worst things you can have is something that's good enough. Same thing, like I'm using Sublime here instead of VS Code. It works good enough, so I never think to upgrade. Probably the same kind of deal. But I do like that this is a little denser. So generally I'm happy with kaze, but there's also a big missing feature in kaze, which is probably the thing that I find most annoying with it, and that's that there's no like switch case or match case sort of construct. So for example, state machines look pretty ugly right now. For example, in the Uart stuff, like this, I hate all these else cases that just have tuples to deal with these. Well, there's two things I don't like here. First of all, is it's this big if, else if, else if, else if, where all it's doing is comparing a state to a bunch of literals, and this looks really ugly. Like I hate this. But I also think it's a good exercise when you're doing something like this to do it the bad way first and find out where the pain points are, and then think about what they would actually look like in context instead of like preemptively trying to solve this problem. So I am happy that I took this approach, but I don't like how this is currently. And then again, there's a lot of these else cases that just return the same tuples, which, yeah, this could be written better. But also a match case thing would make all this stuff smaller, like this if else. But it would still end up being expressions where I would need to like return tuples or something. And also, I mean, this is also might be evidence that I can simplify this logic anyway, and write it, like formulate it all differently. But yeah, I'll go away first, and then we'll make it better later. At least it's working. That's the cool part. By the way, hi to her too. Yeah, at least those kind of like state machine things tend to look better in Verilog because of mutation. And in Rust, you kind of have the option to choose. And if you choose to make everything expressions, you can often end up with the code that's similar that I had there. But you also have the option to drop back to mutating state, which is how you'd write it in Verilog, and that's why it ends up being better. I guess twofold there. One, because you're doing mutation instead of forcing everything to be expressions, and then the other part is that it actually has some kind of switch mechanism. So at least the switch part is something that I know how to fix and have kind of an idea for how I'll fix in my head. The other one, not so sure, but we'll see. It's kind of a fun experiment because this whole kaze thing in general, it's a project that I wanted to do for a long time, but I don't really have big ambitions for it. It's pretty much just like, here's the tool I want to use while writing RTL that I'm testing with and integrating with Rust. So I'm happy with doing it, but It's fun to be a little experimental, I guess. Anyway, I think this is all we need. So then we just need to make the code gen actually work. So I'm guessing if we run this again, I don't think I changed it, but I'll run it again anyway. And we should see the same thing. We should see it just says not yet implemented, but it also tells me that it comes from system verilog rs420. Blaze it. So if you go into kaze, there's a system verilog module. And if we go to line 420 here, this also is written where like a lot of classes and stuff are in this, or a lot of structs are in this same file that I'll break out later. 420 is right here, signal data instance output. Yes, this is exactly what I suspected. This is where it walks the IR, and it goes from the top level code, which in this case is this Uart, and it goes from its outputs and then traces back to find its inputs. So it doesn't really matter which one of these it chooses first. So for example, has errored, I guess that'll get to a register, and that's not a big deal. But for example, TX is output from this module, and then that goes straight to this Uart TX output, which is an output of this instance. And that's exactly what we see here. Instance output. So it hit one of those nodes in the IR. Now, this is not as fun as I was hoping it would be. Let's see. So one of the things that's different here is that so the way kaze kind of works is I generate this IR by basically making these API calls. And then you end up with this graph, and this graph is made up of a hierarchy of modules that might have like registers in it or a bunch of different signals. So for example, if I take the value of a register, that's a signal. In this case, a 1-bit signal, and then I can take that and mix it with other stuff. So for example, this if ends up generating a mux signal that will mux this value versus this value selected by this value. And that's how, like, for example, this has error.value can be mixed with other signals. And same here with write enable, where we generate a new signal that represents this bit inverted. And then we can use that to drive this input. So you end up with this graph of signals and modules and everything. And then from there, we either generate a Rust sim or we generate Verilog. And both of those kinds of code generation, the first thing they both do is they run these validation passes. So there's... let's see, it's down here, I think. Yeah, so there's this generate thing, and the first thing it's going to do is validate the module hierarchy, where this is the root, and then the Rust sim code gen does exactly the same thing at first. And so you can see that they actually both have the same tests, which I literally copied and pasted for both, because I want to make sure that the same tests are running for both of these things. And then the only difference is that generate here comes from it's this generate function for the system verilog module rather than the sim one. So the module hierarchy is validated, and this will do things like find purely combinational loops in the graph and make sure it reports errors. This whole validation thing here finds recursive definitions. So for example, if you have a module and it instantiates another module that is itself, that's bad. If you instantiate module A and that instantiates module B, and then B instantiates module A, that's the same case, but it's indirect. That's the same. This pass will also detect that. Any register in the entire hierarchy that's not driven, we generate errors for. Even if that register would have been optimized out because it's not used, then I still want to do this, because otherwise you can mask a lot of errors by having a register in there that isn't actually reachable from the outputs. And I imagine when like refactoring modules, this would be really useful, because it might be that you refactor some module that disconnects some register's output, but you still want to maintain the logic that goes into that register for whatever reason. And then suddenly later you might hook that register up again. And I don't want a bunch of new errors in case you haven't kept that up to date by not driving some of its inputs, for example. So that's kind of the thought of why I always do that. And then this mem errors, I think it will just check for some errors that are specific to memories that are instantiated in the hierarchy. And then, yeah, it also detects these combinational loops. So I don't think any of this is particularly complicated, but the point is that the same validation code path is used for both kinds of generation, which is nice. A consequence of that actually is that the way I have this set up, it's going to call generate on all these different modules. And so a lot of these are going to get validated more than once. And in some cases, that's actually quite okay because, for example, an LFSR that's instantiated in a different part of the module hierarchy. So this is generated or instantiated twice in this UR hierarchy. And we actually want to validate those separately because it might be that you end up with some like purely combinational loop between the inputs and outputs of a specific instance. And then even though you have the same module, they need to be validated in different contexts to actually detect that and properly report that error. So it's actually okay that I think that gets checked multiple times. And also it's really fast. So at least at the scale that I'm doing this at, which is, I think it's only ever going to reach probably not even 100 modules when all this is done. I think that's quite okay. But yeah, so one of the things that the sim compiler does is it will go and it will collect all these what I call state elements, so essentially the memories and the registers. And that's because it'll propagate from the outputs to those elements, and then it needs to propagate from those elements as inputs backwards as well to find reachable stuff in the graph that we actually need to compile code for. Sorry, I dropped something. And when generating system Verilog, it's a bit different because one of the key difference there is in sim, it will actually flatten the whole graph. So if you have I think I've talked about this several times, but if you have, I'll actually do this in Paint and not in Draw.io. No offense to Draw.io. This is just, let's be quick and dirty here. So if you have module A and this instantiates module B, and then you might have some input here that goes into this, and maybe it's inverted or something, and then this goes out here. Really basic case. It's a lot easier to generate code for this if we actually just flatten this whole hierarchy. So I'm gonna try and make this look like it's like a dotted line. If we kind of do this and then generate code as if it's sort of one unit, it just happens to be a little easier to generate code for. And so we do this for the Rust sim. And there, I guess if I were to talk about why, it's because there might be cases where like an input here, you might have an input here that goes to a register, and then this goes in here, and then there might be some more stuff that happens in here, and then this might output something that's like out here. And in fact, this might even route into the input here if there's like some kind of mux, for example. What's important here is that if we were to create a model of this that actually preserved this hierarchy, then we would have something like struct A, and then it would have a data member that would be some member B. I'm writing this really terribly, which seems really straightforward, and then we might have like the inputs and outputs and registers on this struct as well. But then in simulating this, it's a bit harder because, so let's say we have the inputs, and those will change, and then we would call like this propagate. So this would propagate this signal to here, and then it would propagate the signal to here, and then it might also propagate this signal here. But if you notice, once this is propagated here, now we actually have to, for example, propagate signals in A again, unless we were smarter and actually tracked individual dependencies, which is kind of annoying to do. We can actually avoid doing all of that if we just flatten the whole hierarchy, because since we don't have any loops, any combinational loops ever, we actually know that if this was a flat graph, we would only have to propagate the signals in A. So for example, this would go to here and then through here and into the output, and we're done. This would go to here and to this register, and that also includes propagating this signal, because it's all the signals of A, and then we're done, and then this also propagates. Yeah, exactly, because this propagates through here and out this way. If you go the other way, then it's easy to see actually. Let's do that. Let's pretend I went the other way. So we'll take this output and we propagate backwards, and this goes through this inverter back to here, and we're done. We'll propagate this output backwards. Its value is the output of this inverter, which depends on this input again, and we're done. And then the register, oh yeah, and this also, I guess I drew this really weird. Oh yeah, because this wasn't connected to that input. It was connected through this inverter and then back through here to the value of this register, and we're done. Because this register will not reflect the new value until a clock edge, which is a different kind of operation. So then if we look at this register, this says, okay, we'll propagate this backwards. So this goes back through here, back around, and back to the current value of the register. Okay, that's done. And then that also muxes with this. So I don't know if I explained that very well, but it makes a lot of sense, and it's really easy. And you don't have to sort of track dependencies within this module hierarchy to make all that work. And if we're going to generate sim traces, which is something eventually that I kind of want to do, we can still have information in this module that knows about what this hierarchy was. So we can still generate a hierarchical value change dump where we have that hierarchy preserved there, but then still in the evaluation of this model, we never have to track any of that hierarchy again. So that's why I did that in sim. We can sort of invisibly flatten everything, and that makes our life a lot easier. For generating Verilog, I decided to take the opposite approach. And this is actually, it should be sort of conceptually pretty easy. In fact, it should be easier, I guess, because the idea is that we have, again, we'll do the same A and then B. Since we're not actually having to simulate the output of this, and our target is Verilog, and Verilog also supports module instantiations, then we can represent this whole B thing instead of as the signals that it would have brought up to A. We just instantiate as, and we represent it as the instance itself. So it doesn't matter what's in there. It doesn't matter what the dependencies are. Of course, we validate it for like combinational loops because we want the invariants to be held always, no matter what kind of code you're actually generating with kaze. But then, yeah, it would generate code that represents this register. It would generate code that represents this mux. And I think it was, this goes here, and this goes here, and this goes here and here or something. That and then that, I think I had something like that. I don't really remember. But this should be easy because we represent this as a node, represent this as a node. This would be a node. This would be a node. This is a node. This is a node. These inputs are nodes, etc. And the register is represented as its current value and its next value. Again, our nodes, and then some code there, and then this mux. So anyway, my point is we should be able to just instantiate these instances directly. However, we do still want to optimize things that are not used. Although maybe we actually don't want to do that. Maybe we want to kind of preserve everything when it generates Verilog. I mean, the synthesis tool is going to do that anyway. But yeah, we'll see. Anyway, during that flattening pass for the simulator, it goes back and it sort of collects, it traces from the outputs, and when it sees the output of an instance, it will sort of trace into that instance, keeping track of how it got there as well, so that it can find like all the registers in there and sort of add them to this outer part. Whereas here we actually don't want to do that. We want to collect all of those to make sure that we visited the whole graph, but we don't actually want to generate code for any of the registers that were sort of found, or any of the units that were actually found within this module. We don't actually care about those for generating code for this module. We'll generate those as we generate code for B later, which I think was just sort of two inverters. So then B in isolation is really trivial. This should basically already work. But then A is a little more complicated because we need to handle these instances. So I think, let's see. Luckily, I think at this point in the compilation, maybe I can't really assume much here, because I think, let's see, down here. Yeah, I do have the state elements class, which again collects all the registers and the memories that are in use for a given graph. And this state elements thing, again, is built to sort of flatten the hierarchy for SimGen. And I decided to start by reusing that in in the Verilog gen, but that might have been a bad idea because first of all, I kind of want to include instances here as well. Yeah, the more I think about this, the more I think it might just make the most sense to not try to optimize any of this anyway. Because the only reason I really want to sort of walk through these outputs to the inputs in the first place is so I can track dependencies for generating sim. And it just so happens that if you end up pruning the graph by not reaching it from the outputs, you sort of get, as a byproduct of that, some kind of optimization where unused stuff is just gone because you never reach it. Which again, I'm quite happy to have for sim. But for Verilog, we don't really need to do that. We can just take the module and, hey, Lord Kipo, you can just take the module and sort of generate it as is. And in that sense, it really doesn't make sense to go through and find the reachable state elements. Really what we want to do is take all of the elements that are on the module itself, and I believe in the current IR, current graph thing here, which would be an actually module, I think, yeah, this stores registers, instances, and memories. So we should be able to just make a map of all of these for the Verilog gen. Later, Cable, we are working on Verilog code generation for kaze. So I've already started a bit of this, but we're gonna fill in some holes such that our Uart test is almost entirely implemented in kaze. And the main benefit of that is to use that as a stepping stone for the entire xenowing. So yeah, so I think I want to move this state elements thing back into only the sim gen, and then we'll maybe make something else for the Verilog gen. I think that makes sense, which means we're gonna have to move around a lot of stuff, but that's fine. So going into, I'm just going to do this. It's easier if I do this in Explorer. So yeah, state elements used to just be in sim. So we'll move that back. And we're going to have to move a lot of stuff here. Maybe that's okay, except I think this will be wrong because now this doesn't actually make sense to gather stuff like this. Module context I think has to be at that level still because I think the validation uses that as well. Yeah, it does. So yeah, we're going to remove state elements from here. And again, I might add a structure that's going to be similar to that. But now there's a state elements thing in the compiler, which just goes away. So now the compiler really only has this expressions thing, which is perfectly fine. I'll get rid of this state elements one here. Yeah, we actually do want something like that still. So I don't know what I'm going to call this yet, but we can do, for example, might just end up being the compiler, but I have a feeling it won't be. Yeah, we'll call it something else. Let's see. I don't know what to name this. Because it's not just going to be a collection of signals. It's going to be like mappings as well. So for example, the state elements thing, we actually had these sort of parallel structures for register and mem. And we're also going to have one for instances here. I'm going to call this something. And that's going to be good enough for now. And then, yeah, again, here we need, I know that this is going to need these because we're going to have some mappings from structures in the graph to structures that are only existing in compile time. Like that. It's going to be something that regs, which should have an error. Let's see. Yeah, because this had maps for all those, so let's actually just do the same thing. I don't mind more or less copying this stuff. Super. Yeah, that's fine. I actually think since state elements is only under sim, we can just make these public. Like that, which I kind of like. Yeah, foobar would have, I guess, been more conventional. I do like foobar too. Yeah, so from here, we have this register data, and I think on state elements, yeah, regs goes from the signal to the register itself. Let's copy this. I also had these in alphabetical order, so let's do that too. I think also I'm not going to make any of this public until I need to, so we'll do this. And then we also need instances here. Like that, and then we can do instance name. Although I actually don't think we need extra names for these anymore because we have validation passes earlier in the compiler to make sure that these are unique. And if we're not going to flatten anything, then we have no, because one of the reasons why we need new names is if we generate code for, say, a module A that looks like this, and it has a register in it that's called A, and then this has an instance of B, which might be called B, lowercase b, like this. Now, if B has a register in it that's also called A, that's bad if we flatten this graph. So we actually end up prefixing these names that are in these instances. And that way we can guarantee that they're always unique. So we actually don't need to do that when we're generating code for this stuff if we know that this is already validated to be correct, because we're not actually flattening the graph. So we know instance names are going to be unique, we know mem names are going to be unique, and we know register names are going to be unique, I think. Registers are actually a bit special because we need the value name and the next name, so we'll keep that. But I think for mems, we're okay. And for instances, we're okay to just keep their default names. I'm going to keep these as additional structs because we may need to do something more clever here. Yeah, we'll add an instances thing here. That goes again from, yeah, also this doesn't need to be in a specific context. So these go away too, these tuples, which is nice. And then, yeah, that'll be. So now this, as it is currently, this feels a bit silly. Yeah, also we don't need this arena thing anymore, which is nice. And same for the signal expert thing. We probably don't need the context anymore because they're all going to be from the same context. So this gets nicer. And here, I don't know if we even need to have this lifetime here. Oh yeah, we do, because it's still a reference to that. Like that. Yeah, we no longer need this context at all, actually. Yeah, I think that's okay. Of course, that's going to cause a lot of problems, which is fine. I think we just go and search for these. Oops. I'm going to need this root context. We are going to do something different here. We'll do this. And this also, again, doesn't have the context, so we just have this, and then we can also do something regs values, reg. Again, no context here. And no context here either. Which means we can ignore that to do, which is nice. I like that. Again, no context here, because we're compiling all of these signals within the same context. Yeah, then this didn't have new, which I think just was like this. So I'll just rewrite that. Does that work? Do I need to have the lifetime parameter here? I do. And this will just do something, and that'll be instances, hash map new, and mems, hash map new, and regs, hash map new. Okay. And EQ and hash don't work here. Probably because I haven't implemented EQ and hash on instance, which I can just go ahead and fix. But I'm actually going to wait because, well, I do actually think we're going to need additional names here because I think we're going to have to go through all of the inputs, for example, and make a new map. So for all of the inputs, we're going to have new nodes that we hook up to the instance, and then I think that'll be stored here too. So I actually do know that I'm going to add more stuff to this instance structure here. And mems might work the same way. I'm not entirely sure. We don't really have to handle that today because the module that we're trying to generate code for doesn't use any of those. So the key is the signal here, which means it may not actually make sense to have a separate key anymore at all. So I think I might just do this. So does this work to do that? I think it should. No, it didn't. Oh yeah, because we want the reference as the key, so we need to take a reference to the reference to make that work properly. That's actually okay. So this is signal.clone, which again, I think only clones the reference. So I think this is actually what we want to do there. And then again, this is signal. Can I just do this again? I don't think I can. I think we need that again. Yeah, and I'll go ahead and implement hash and EQ for this. I did the same thing for signal. So we'll just copy all these and get those on instance as well. We need hash and hasher, which again we'll get from here. And yeah, signal doesn't make sense here, but this will be instance. And it's all just reference equality here. So that's what we want. Now we no longer use pointer or module context, which is nice. And this still will not generate any valid code. But it might actually build. No, it didn't. State elements for compiler. Yeah, that makes sense because this compiler in here is, we don't want state elements, we want super state elements. And now there's a context arena here that is no longer used, and so it can't infer the type of that anymore. Because we're not creating contexts since we're not flattening anything. So yeah, now we can get rid of the arena thing here, which is nice. I don't think we're ever actually going to need that. We'll see. We may want to rename these lifetimes then too. We'll see. I think I actually do want to do that. Yeah, then nothing's ever used, but this should still run, I think. No data, register data. public interface. What made that public? Is it this one? Wouldn't have thought so, because this is not public. Might be this. Yeah, none of this should be public, actually. That's probably it. Still not enough? I don't know what else is public here. Well, that's true, but that shouldn't matter. That one needs to be public, because that is the actual interface there. Oh, to say sim state elements, doesn't it? So that would be here. Okay, I don't know why. State elements is public here. It shouldn't be, because of this mod here is not public. And here we are. Did I change the visibility of this? I must have. Maybe that's why I had this great stuff here. In fact, this shall be super if they're not used anywhere else. So admittedly, I'm not entirely sure why that was in the public interface, but whatever. Because again, this whole state elements thing, this should have been state elements. It's not public from here. Well, sim is a public module, but then state elements inside that isn't. So I'm not entirely sure why, but whatever. I'll just accept it. Okay, but what we actually want to do now is in this Verilog thing, we need to populate this something structure. And I'm actually wondering if we want to just give this the module. I think we do. And then we'll not have it be mutable. And this probably doesn't need to be used outside the compiler. Actually, yeah, I do kind of want it to be. So access directly here. Yeah, we'll keep it that way, and then we'll make something up here, take that as a parameter. That's what we'll do. Do something like this. And then we can do, let's see, for instance in m.instances.borrow .iter. And then we'll do instances.insert. Something like that. do these all separately. For the register thing, I think we want to do this a little differently. I do that in that gather function, don't I? In this other one here. So I just generate them like this. Let's copy this. I think that's okay. It's not terribly important. Yeah, so let regs is hash map new. We'll do regs here. For reg in m.regs dot borrow dot iter. Just to be sure, check module. It's called registers here, which is why I checked. And then we'll do regs dot insert. And this will be reg, and then this will be register, and let's see. This had data, which will be reg.data. Has value name, which we will come up with here. So value name and next name. Module not contain that? Is it registers? It is registers. A field name on the signal. Where is that handled in there? That. So what does this do again? Oh, there's no name on signal data, which is signal data. Oh, really? M registers is a signal. Okay, not ideal, but that's fine because we can do this. Match reg, and if reg.data, and we'll either get, we'll do this first of all. I guess we get signal data register, and then in signal, what do we have there? Called reg here, so should really make that more consistent, but that's fine. And then this will be data. So then we can do data.name data like this. Yeah, because I need to move all this up in here. Okay, probably just changed that in the wrong place then. Okay. Yeah, so now we should be generating names for all the registers. We should be generating names for all the mems and all the instances. Although, again, I'm not entirely sure we need this, but probably do. We'll have to see. We may not be able to have this as a member on the compiler struct here, because I think we're going to need this to be mutable. Maybe we'll end up doing some internal mutability or something. Not entirely sure what I want to do here. Maybe it makes sense to just put all this on the compiler actually anyway. Probably does, because I don't think we're going to use this anywhere else. Yeah, I'm going to do that, actually. Make all these fields on the compiler. And then I never needed to name it. That's great. Yeah, because there's these signal expressions, which are going to map to expressions, and then we have the stuff that we'll collect. I think this makes sense. I guess we can do this. That wasn't that well thought through, but that'll be fine. Like that. And then we can do this, where we have instances, mems, and regs. Yeah, no, this doesn't make any sense. Which is totally fine. I think in the end of this, we'll end up with the Verilog compiler here being a lot simpler than the sim one, which is kind of what I expected. Because now this can just do compiler.regs.values, which is fine, or even C. So this will take the module as input. Ooh, that's why I had these separate. Crap. That's why, because yeah, this is where it's like declaring nodes for the inputs to the registers. And it would do the same thing for memories and stuff. We need to borrow the registers that we're generating stuff for. And we also need to have the compiler be mutable. So we might have to do one of these like we do with assignments. Pass it in that way. So something does actually become its own object again. Okay, and then there's no field here called something. I'm going to go back and forth on a lot of this before this is done, and that's fine. It's not really that big a deal. is going to be mutable too. This is kind of weird. Here, I make a new structure of those registers, and then I use that everywhere. That seems a bit strange. Ellipsis, thanks for the follow. I think I might be on the wrong track entirely here. Because so we need to know the register names, like their compiled names, when we find a register, for example, for compiling stuff. So whatever structure that is, this compile signal thing is going to need to see it. So we might end up with another field here. But I think that's fine. Should be. Yeah, I'm going to do that, actually. We're going to have something. Yeah, and then we actually do need this other. I'm going to call it something like this. It's great. Or actually, no, because we don't need it there. And here, we don't need this to be mutable, so we actually don't need to have a lifetime here. So we just do this. Hey, Amaran. So now this, of course, causes a lot of problems because it's not that bad. I think that's just going to be this. Yeah, maybe that doesn't need these. Then this is going to be something.regs, for example. So it does actually need the lifetime. That's fine, because we can do that here. And then we need to make sure that this is something. Ugh. And something graph signal. That's wrong. Oh, I know why. Because I did that. There we go. So do I still need this? I think I don't. So I think that was the issue. Yeah, we're good. Whew. Yeah, so stuff is not implemented now. It's 477, which I think is the same line. But we can actually look into implementing that now. So what do we want to do here? We want to do something like this. That's what we want to do. This is why I think the initialization of something actually shouldn't be up here. Should be something like this. Oops, like that. I don't know that we need this to be mutable, so let's keep it not till we need it to be. What is up here? Yeah, that's that stuff. Worry about that later. So let's see. I'm also actually going to remove all this stuff for memories, because I think it's better that we take that later when we actually deal with that, since I keep running into it. Yeah. So we need to fan out here a bit. We need to, let me show you what I'm thinking. So this is what an instantiation normally looks like when you just write it in system Verilog. You'll have these nodes here, these variables here that represent essentially signals that you're going to fan out of this instance. So for example, we have this data here that we're going to assign to this write data, and then we use this node later. So essentially all the inputs and outputs we need to generate nodes for like this, so that then when we generate the code, we can hook them all up like that. And then we can also generate, have the compiler generate expressions that actually assign values to these in the case that they're just inputs. So that's something we need to do. We need to, that's one of the reasons I want to have this initialization down here, because we actually want to have this assignment context thing here. As you can see, I compile signals for all the outputs. I also want to have this up here, for example. Or maybe I don't. I'm not sure. I guess what we need to do is have names like this. So I'm actually going to take this something here. I'm going to move this stuff for now while I'm just working with the code. I like to do this where I just kind of throw everything in one module while I'm working with it and then split it up later, because now this is right up here. So let's see. We have this instance, and then I want to have some kind of map where I have, for example, input names. So the name of the input to the name of the input like declaration, and same with outputs. I think that's what I want to do. It just used the graphs here, they're all just custom structs. In fact, or no, I do use a lib. That's a good point. I use the typed arena library, and everything's just stored there, which is a really natural choice for this kind of thing. And so kaze relies on that internally. And so when you use kaze, you create a context, and a context really is a collection of a bunch of typed arenas and not much else, actually. Actually show that. A bunch of arenas, and then this this map to these modules with internal mutability here. Not super pretty, but definitely works. Yeah, I guess I just generate these then. Oops. Now I think an instance, it has the inputs that are driven, which they all should be driven in this case. And then the outputs, because it has this module, which is the module that this belongs to, which is more about object lifetimes. Then it has this instantiated module, and this is the one that we need. Oh no, I'm sorry to hear that disused. So then we need to go to module. That's in here. That has these inputs and outputs. So we can do for input in instance dot instantiated module dot inputs dot borrow dot iter. And I think that's, string and a signal. So really we just need the names actually. So we can do this name underscore. And we do input names dot insert name dot clone. And we can do, I've kind of taken this convention where I reserve underscore underscore for stuff like this. We can do something like this. Should work. And so then this can be the instance, and that should have a name, which it does. It's dot name, and then we can do name. So that might be one of the input names. And then we should also do this for output names, which I think module also just has outputs like that. And we'll call this output. And this will go into output names. Oh, that's huge, Dark Second. Oh, by the way, I'm so pumped for Doom. Of course I pre-ordered it, so I'm going to play it ASAP tomorrow. After work, of course. Let's see. I'm also just going to reorder the stuff because I think that's nicer. But yeah, now this like instance struct actually makes sense because we have these input and output names. So the nice thing is now when we actually compile this instance output here, we can do something meaningful. So if we go to the sim compiler, which I'm really still glad that I put off system Verilog gen for so long, because the sim compiler is by far more complex. So I can just take a lot of patterns that I figured out for that one and sort of backport them. So the instance output has an instance and then the name, which I think is the name of the output. So this is the cool part. Now we have something, right? So we can do output is, well, that doesn't really matter, does it? Equals something dot instances instance. I think we need to do that too. We need to make an expression. And so I think all we're going to do is compiling the signal, which we actually don't need to do here because we're going to do another node that represents this. So I actually think we do expref, I think is what I called those. Yeah, ref, and that's just the name. So name is going to be the instance dot output names by name. And then I think we need to clone here because it's a string. And we should be able to take a reference there. That might just do it. Yeah, and this actually seems likely to me that we never actually use this instance that's on here. I'll get rid of that preemptively. And now this doesn't need a lifetime parameter, which is kind of fun. And the input names with these, I think, will be used because we need to generate nodes for those, which we'll deal with later. I don't have a VR headset. I want to do that. I've been thinking about getting the PlayStation VR so I can use my PS4 more. By the way, I'm loving the spec videos that are coming out about the PS5 and the Xbox Series X. In particular, I was really pleased to see that there's a hardware implementation of Kraken in the DMA unit of the PS5. That's pretty cool. Yeah, that's true, Zalkwar. I do have VR headsets. I have several Virtual Boys. Good points. Believe me, that is one immersive experience. I'm really tempted to make like a spec reveal video for the Xenowing when it's ready, where I do it all pretentious, but it's all shitty. After seeing these, yeah, I gotta say I'd probably go for PS5 too of the two. Although I'm more charmed by the look and what the internal design looks like for the Series X. Though to be fair, we haven't seen the PS5 yet. We've only seen those ridiculous looking dev kits. Unless the actual look has been revealed, in which case, please link it to me. Yeah, I could do like silhouettes of people at the bottom of the video, and then like edit in shots of just like crowds cheering and people clapping for different features. That'd be awesome. I'm super into that, you guys. Okay, so this got generated, but I don't think this works at all. I mean, you can see that this has errored thing actually generated valid code, and we have some temps here, but yeah, none of the stuff we actually added is generated here, and that's probably my fault. For example, here, yeah, I go through the registers and I add node declarations there. And I need to do this for other stuff too. Yeah, I definitely need those awkward third-party developer segments. Those are so ridiculous. It's funny too because they're touting like hundreds of gigs a second, or what were they touting? Not hundreds of gigs a second. That was stupid. But or was it? I don't even remember. 5.5 gigs a second, for example, I think was one of the numbers. I think I calculated the max bandwidth for the DDR on the xenowing. It's actually like, was it 1.2 or something? So I actually calculated that at one point. Yeah, it's about 1.2 gigabytes a second. So only about a fifth of the PS5. That can't be right. Oh, that was disk bandwidth, wasn't it? It totally was. Yeah, 5.5 gigs a second disk bandwidth. So I get a fifth of the PS5's disk bandwidth to my main memory. Yeah, PS1/5, that'd be great. Yeah, I did go through and actually calculate all this bandwidth stuff, which was important because I wanted to see, like I wanted to figure out what kind of resolution I should target. So I decided to do 320 by 240. What was my bit depth? 32, I decided. All right. I don't remember doing these calculations, so I'm glad I still have them in the spreadsheet. Or actually, I do remember doing them, but I don't remember what the results were. Yeah, the Jaguar bit stuff was so ridiculous. And then they had all these do the math ads. Wasn't that what it was? It's just so stupid. I love it. Yeah, so we put together all these instances and mems and regs and everything on this structure. And then we start compiling stuff. So we compile the outputs. From the outputs, we compile from the regs, and then we should compile from the instances as well. I think here it doesn't make sense to have another registers thing here because we might as well go over the values of the storage there. So I'm actually going to remove this. Something regs values. And we can just do that same thing here. Oh no, we do want this. This is going to be something.regs. That's quite okay. But yeah, we'll basically do the same thing here. So for instance, in something.instances.values. So we'll do for these input names. Yeah, that's what we need to do. We need to output a node declaration for each of those. So for actually, we need to go over the original instances stuff for this. So maybe calling this instance wasn't a very good idea. So this instance data. Ugh. Or instance node names, we'll call it that. Right, so now what we can do is this. And the compiler, I think, complains about this. Yeah, instance node. I hated how I named this, actually. Yeah, exactly. Dark second. These are so ridiculous. But I also love it. What a ridiculous device. We can call this instance decals. I still don't like this though. I'm gonna do this. It's stupid, but I'm gonna do this. Actually, we can still call this instances for this one. Let's do that. Just call it that. Yeah, we'll do that. And then here, in something instance, so this will be the instance and the instance decals. That's really all I wanted here. And then here we can do, let's see. What's I trying to do? Yeah, I want to do this. So for input, actually we'll do this. This will be the like this. We really need to output a decal for this one. We don't need the original name in this case. We will actually to generate the assignments for it. So actually we do want to iterate over both. Then we should have everything we need to go through stuff. So then we'll do node decals.push because we need to declare one of these nodes. And for this, we'll do the name is going to be the decal name.clone. And the bit width is going to be the actual input. So on the module, we should be able to get the signal and then get its bit width. That's what we want to do. So that'll be instance dot instantiated module dot inputs dot borrow, and then there we need to insert the name of the input dot bit width. Does that work? Great. And this isn't complete. This should just output the declarations, but it shouldn't actually have any assignments for them. But I still want to see what the generated code looks like currently. And by the way, I won't stream for too much longer. Yeah, so here we see, here's all these declarations for inputs, for modules that we, or for instances that we do not have yet. So we'll get cooking on that too. So that's this next part where we need to let expression is c dot compile signal. And here we need to compile this input here. So this is actually what we need, first of all. And then this will be signal.bitwidth. And then we compile the signal and we give it something, which I still have yet to rename. And then these assignments in case it needs to generate any temporaries. Well, it compiles that, and then we're going to actually push an assignment to this decal, where again the target name is going to be the decal name.clone, and the expression is this expression that we just compiled. And that should cover all of the inputs, I think. Yeah, so now we have, for example, this shift enable is equal to the shift enable signal, which exists nowhere. And I don't know why that is yet. But I'm sure we can figure that out. But for example, this one is a better example of something that worked, where we had this signal that we're going to tie into that RX input, or input RX, or sorry, the RX input of this UART RX module. It assigns that value to RX, which is this incoming wire here. So that's definitely what we want. And I'm a bit surprised at this shift enable thing. Can't really explain that yet. Try and put shift enable. It's weird that this ended up with this as an expression. So I don't know why that is yet. But I'm going to ignore it for now, and maybe the answer will become obvious as we get farther with this. Ooh, also, I just had a thought. No, we still use output names here. That's good. Oh, wait a minute. I think I might just be using some wrong names somewhere. Or actually, I'm not sure. Name is name.clone. Name of an input. Yeah, that's different. So if we go in here, shift enable for either one of these is equal to this read data valid signal or this write enable thing. This just seems clearly wrong, actually. That these inputs got this value. I have a feeling the way we've compiled this is completely wrong. Here. Oh, right, yeah. So this compiled the signal as seen from inside this instantiated module by doing this, which is wrong. Instead of getting the instantiated module's input, I think we need to get the driven input for the instance. I think this is what we need instead. And here you have the string name and the signal here. So I think this is correct to determine the bit width, but it's not correct here. So here we need the instance.driven inputs dot borrow name. That would explain it, because that's where that actual string came from. It came from the definition inside that other module. And now we should see this makes a bit more sense. So now this is this output data valid thing here. And again, this is an output that has no driver because this is going to come from an instance that we don't have yet. Same with this output value here. So this looks a lot better. A lot better. Hazard and hazard next. Yeah, this is looking nice. Thanks for the sub, Yan Moran. Really appreciate it. Yeah, so here we compile all these expressions and everything for this input, or for this instance, and then later we want to generate the code that will actually contain the instance. So we'll do that here. If something .instances.len is greater than 0, then for we want the original instance for the name. So yeah, we'll do instance and instance decals is what we did here, isn't it? Yeah, it is. Like this. And so then we want to generate code that more or less looks like this. So we'll generate the type name first. And this will be the type name, and then the instance name. And we'll start with this, and then we'll also so yeah, instance.name is the second argument in the type name. So instance.instantiatedModule.name there. So we'll start with that. And here we go. Now we can start seeing that these are starting to show up, which is great. Also, while we're at it, I've been wanting to add new lines after every register, not just after the last one. So we're going to do that here. And I'll also preemptively do that here. At the end of every instance. So we kind of end up with Verilog where all these declarations of everything are scattered around a bunch, but I don't care. We could always reorder some of these loops and stuff to try and put these more in the same place if we want to. In fact, I kind of do want to, actually. Especially because we know, for example, I'm going to comment this out, the instances. So for example, for registers, here we add no declarations for the register. Well, actually, I do kind of want all those in the same place. Yeah, never mind. Never mind. This will also be ugly, but who cares? Yeah, so now I actually think there's a valid, but they don't wire up anything. So we need to wire up reset and clock. We know that for sure. Now, again, I have some notes about where it does that here, where I say make conditional. So I'll steal that too for these. But right now, we'll just do this. Like this. Clock. Then if instance decals dot input names. I really should be using is empty here, shouldn't I? Instead of using the length. Check for some more of those, actually. Yeah, and I have all this stupid logic here to determine if you need to add commas and crap, which I hate. But whatever. Probably gonna end up doing the same thing here. Which is, it could be worse. Anyway, we're always going to do append line, comma before every one, and then we're going to do w.append indent, and then append this stuff. And for here, we'll do format. Dot this. And so this dot is the name of the input. Yeah, because we need to do this also for... What was I doing for these names? Name, decal name. And the name is here, and the decal name is here. And I didn't do this right. That's probably the issue. Oops, and I need to... What's this one? This one, and this one. So this probably hooks up all the inputs we need. And we'll do the same for outputs. That looked really dumb. And I think I know why. I think this needs to not append line. This would be append. And then w dot append new line. Append, and this also is going to be append, and then w dot append new line. Almost. And I think that's because the one that did clock should not be append line. That's w dot append indent, and w dot append. And I think that will give us more or less the formatting that we want. And I might change this later too. But for now, we'll just stick with this. There we go. Reset clock, and now here we have enable and data. And these are, let's TX. So these are inputs, and you can see that they're defined up here. And then we actually give values to them down here, which looks great. And then we want, for example, output data valid, which is not declared here because I don't think we've done outputs yet. We still need to declare nodes for outputs, and we need to hook them up here. So we'll do that next. So just like we did the inputs up here, we'll do a similar thing for outputs, only we will not generate expressions for them. We will only generate declarations. Output names. So it'll look just like that, which is great. And this should also not be inputs. This should be outputs. Is that how that works for instantiated modules? Or for modules? Outputs signal. Yeah, that makes sense, I guess. Okay, so that should give us the declarations, and then And we do this here. And this will be exactly the same here. And maybe we want to zip these, or not zip these, concat them, do the same logic. Or maybe not. But now we should have decals. So for example, data valid should be here. Yeah, so here's the outputs for the instances. And we can see it's hooked up here. And then used down here. So this looks great. I'm going to venture to say this might actually be correct. So then what we're going to do is go back to Vivado. And we're going to add a new design source here. So if we add sources, add a create, we're going to add a file. And this is going to be xenowing RTL generate. Oh yeah, this is already there. So actually we don't have to add anything. And you can see it even actually found it. So then we run synthesis and we see if this actually works. So now it's running. I like to look at the log. And if this works, then handling memories is going to be pretty easy after this. So I think this is going to be a good approach. Should be very similar. It's looking good. It feels like it's getting quite far. Complete. One warning, and that's this no constraints thing that I keep seeing anyway, so screw that. And I bet if I now generate the bit stream, we can go all the way. That'll run the implementation. While it's being implemented, we can open the Synthesize design, poke around a bit. And I want to look at the schematic for the Synthesize design. It's going to be not the most easy thing to read. It seems to be the case. This is taking a while. Oh, here we go. But we should see, hopefully, nothing surprising if we just poke around a bit. Yeah, so here's the schematic here. We can see there's these sync chains, and then there's this UART thing here. And so yeah, we get the reset one. We have the clock. This out is named badly because it comes from this RX value, and then we have the LED and TX, which is the outputs of there, which makes sense, I think. Again, this is called has errored here, so it's a bit weird that it's called LED, but I think that I noticed that things get assigned weird names all the time. And then, yeah, we have this reg has errored. We have the TX LFSR, the UART RX, and the RX LFSR. And they look good, I think. There's also like comparison logic for this ended up in here. Not going to really look at this, except I do kind of want to see. Yeah, you can see has errored and reg data valid all come out of here. So it ends up being a bit messy in this schematic view. But yeah, I agree. This looks pretty reasonable. So I'll just close that and wait for it to finish everything else. And in the meantime, I'll pull up Tenagra again. And bitstream generation worked, so we'll open the hardware manager there. Go in here, select from the Xvc server. And I'll go ahead and open that. And I always have to do this open new target thing. I've noticed when I try to reuse the old ones, it almost never works. At least not if I've had to close Vivado, which happened a lot this weekend because it crashed a few times. There we go. So now I should be able to program this device. And I'm going to do that. So there's this top bit thing here. So it's programming. And the other thing I have open here is this Uart check program, which is supposed to check this actually works. Now it won't if one of these is if these are started in the wrong order. So what I actually have to do is I have to hold the reset on the device while I hit enter here and then let go reset. And now you can see it starts working, and this is exactly what we expected. So that's actually great. Now we've moved this over to, we moved this test code, which was here, to here, and it worked first try, which is great. I'm actually going to delete this. And the actually best part about this is not necessarily that this particular module is now in kaze, but we used it to figure out how like instantiations would work. And it seems to be correct. So that's fantastic. Now I do probably want to do some cleanups to this code, so I don't think I'll push it as is. But yeah, I'm very pleased. This is great. And I'll probably just let this run for a couple hours for good measure, just because again, this Uart stuff is going to be really critical for the whole system. If that's kind of like literally the lifeline that I have to connect to this thing. So I'm happy to test it as often as I can for as long as I can. But yeah, this seems pretty reasonable. Can't complain about that. Code isn't super pretty, but I don't care at all. I'm a bit surprised actually how some of these decals are down here and some of them are up here. I don't understand why they ended up added twice actually. Decals, and then we have all these instances, and then later it seems that these oh yeah, no decals and these assignments are separate. That's what it is. Because assignment ends up with a bunch of decals on its own for all of the temporaries that it creates. So I guess I just output those later. I'm okay with that. That's fine with me. But yeah, this is great. I think I'm just going to go now. Thanks guys for hanging out, and I'll see you next time.